Afternoon.
Hello.
Hello.
Excuse me?
Just saying afternoon. Okay, let's see. Which screen are we going to share? We'll share this one. There we go. Okay. All right, you should be seeing PowerPoint notes in a blank canvas next to it. Is that what you're seeing, folks? I hope.
Yes.
Good, good. Yeah, I've got three screens here operating. I need to sort it out. All right. How are we doing here for time? Another minute, I guess. All right. Okay, 12:30. Okay, I'm going to ask you all to mute, please, if I hear somebody's got something going on in the background. Okay, so the other day we were doing stuff to do with stereochemistry of Sn1, Sn2 reactions. What I want to do was an example from an old test now, and show you exactly what's going on with how you would answer one of these on a test. And just to summarize what I had talked about the other day. Now, what I had said was that when you start off with something that's, well, let's say it's Sn2, then we know that R will give S and S will give R. All right, somebody needs to mute. I don't want to have to hunt through and see who it is, but somebody has to mute. Thank you. And for Sn1, R gives R plus S, and S gives R plus S. All right, so that's the main piece of information you need here in order to be successful with this kind of problem. And then, of course, we have to be able to apply that, or apply that logic to the question we're actually talking about. So let me see if I can find my cursor here. Whoa, there he is. All right. So I'll drag the test over here. Here he is. So you should be seeing test 2 here. And I'm going to scroll over down here to number 8. There we go. Okay, so there it is. So what's important here is the kind of reaction we're dealing with. It says, draw the product or products and name of products and reactants following Sn2 reaction, include all stereochemistry. So I'm actually going to do both Sn1 and Sn2, but I'll do Sn2 first because that's what it says in this problem. Okay, so let's go ahead and see how we go about doing that. You'll notice that if you're looking at the initial compound here, the lowest priority group, which is clearly the hydrogen, is not in the back. Right, and that's important. It's important to note that. What that means is I can't look at this and be able to tell straight away whether or not it's R or S. I mean, that's going to be really the key there. All right, so we're looking at Sn2, which means we're interested in having only one product. How I know it's Sn2, it says so in the problem. It's gone off the screen though. There it is, Sn2. And Sn2 is characterized, as you can see above, by a single product and a reversal of stereochemistry. We do know that there is a substitution going on. So the Cl will replace the Br. We know that for a fact. But the other thing that's going to happen is that the stereochemistry is going to be inverted, which means that I need to switch. It doesn't matter what, but any two of these groups anywhere on here, I can switch them and end up with the opposite configuration compound. Now, the thing is, and this is the smart play, is to locate the hydrogen, which is going to be the lowest priority group, and have that one switch into the one that's in the back. Now, the one that's in the back is always going to be the one that's dashed, I'll point at it here with the arrow. That's in the back. So the smart money here would have me take the hydrogen and switch it with that grouping so that I end up getting the opposite stereochemistry. But then I'll be in a position to be able to get the stereochemistry of that product. Of course, the other thing I'm going to do is replace the Cl with the Br. So that's what I'm going to do right now. So I'm going to do two things. I'm going to put the H into the back, and I'm going to put the group that was in the back where the H was. I'm going to replace the Cl, replace the Br with the Cl, and the other one's going to remain the same. Okay, I'm going to stop here for a second. Does anybody have any questions about what I'm doing there and why I'm doing it?
Yeah. So when I'm looking at this, how I would put it in the back is I'd rotate the molecule a little bit counterclockwise, and it would put the 3 carbons where the Br is, the Br where the hydrogen is, and the hydrogen where the 3 carbons were.
Okay,
putting the hydrogen in the back.
All right, but what you've got to understand, Jonathan, is if you do that, you're not going to be changing the stereochemistry. And it's important that the product we end up with has to be the opposite stereochemistry to the one we started with. And the way we're getting the opposite stereochemistry is by simply switching 2 of the groups. So rotating it won't change the stereochemistry. Switching 2 groups does change the stereochemistry.
Okay, I think that's where I was confused then.
All right. So once we've done that, we've achieved both of those goals, right? So we do 2 things at once here. We switch 2 groups and do a substitution.
And what are the rules for switching the groups? Are there any?
No, you can switch any 2 groups you like.
Okay, thank you.
And you will change the stereochemistry. Now, but the smart play is to change it so that the lowest priority group ends up in the back.
So you'd kind of be looking for where the hydrogen is, making sure. Okay, and that would be your first look for switching a group. Okay. Okay, thank you.
That's what I would do. So switch 2 groups and substitute. Right? So you have to do both of those things.
And this only applies to the SN2, correct? Not SN1, these rules?
Right. Well, it's applicable to the SN1, and you'll see why in a minute. Okay. How it would be applicable to that.
Okay, thank you.
So now that we got the hydrogen in the back, we can actually figure out what the stereochemistry is of this one, and by looking at the priorities. Now, looking at the priorities, we got Cl, we got C, and we got C. Can you see my cursor or not?
No.
No. Okay, no, that's right. You don't see it on here. That's a Cl. That's going to be 1. This, this grouping up here is going to be number 2. And the grouping down here will be number 3. Now, the reason that this grouping is number 2, what I'm pointing out with the arrow, is because it's branched, whereas number 3 is not branched. So that makes number 2 higher priority. Once we've got that, we can look at the 1, 2, 3. Now, remember, you're ignoring the 4. I'm not even writing 4 in there, you'll notice. I'm just leaving that be. I'm only interested in the 1, 2, 3 order. Some people wonder, you put the 4 on here. Well, how do you handle that with the order? Well, you don't. You just ignore it. So I don't even worry about it. So 1, 2, 3. It looks like it's going in a counterclockwise direction. I'd call that S. All right. Any questions? I'm going to name these in a second, but for now, I just wanted to get the stereochemistry. So that's S.
So I do have a question.
Uh-huh.
So is the first so the stereochemistry is supposed to switch between both molecules, right?
Yeah, that's correct.
So if I was looking at the first molecule, I'd label, oh wait, but we can't because the hydrogen is not in the back.
That's exactly right. This is why we're doing what we're doing.
Right.
Now, let's say the hydrogen was in the back on the first one. Gosh, that would make life pretty easy then, wouldn't it? You could go ahead, you could find the stereochemistry and know what the stereochemistry the other one was. Just switch any two groups except the hydrogen, because the hydrogen's already in the back. But generally speaking, it won't be.
So if you switched it with the 3 carbons again, wouldn't it still be bromine 1, the 3 carbons 2, and then the 2 carbons 3? And it would still be counterclockwise?
No, because, well, I can't tell from this because the hydrogen's not in the back.
You can't just switch it.
Well, I mean, I could rotate it. But I don't want to do that. I'd rather make my life easy and figure out what the product looks like and then get the stereochemistry of that. And then also know that if that's S, that means this one has to be R.
All right. Yeah, I'm just trying to figure out why the first ones are besides that reasoning.
No, well, that's the only reasoning that's important, Jonathan. The fact is it has to be opposite to the product because we know that because we switched two groups.
Mm-hmm. Okay.
So that's the logic there. So the name of this, what you'd have to do is figure out the longest chain here. And sometimes it's helpful for something like this to go ahead and draw it as a line structure, just so you can help to identify the chain. Let's see, that's going to look like that. Yeah, so as a line structure, it would look like this, which would mean that it was effectively, let's see, it's a pentane, so 2-methyl 3-bromo pentane, but the bromo has to go first, so it'll be 3-bromo 2-methyl pentane.
Do we include the R and S in the naming?
You do, yeah. So what you would do is you would do R with that and then S with that. Now you don't, because there's only one chiral center in the molecule, you don't even really need to put, let's see, the chiral center would be where the BR is. So it'd be 3. You could say 3R if you wanted to, but you don't have to. You can just say R and S. But you could say 3R or 3S if you wanted to. It's not really necessary though, because there's only one chiral center. All right.
Can we do another example from one of the other tests?
Yeah, hang on. We will in a second. But hang on, just one other thing. It's bromo on the first one. It's going to be chloro. I misspoke here. It's going to be chloro on the second one. So it'll be 3-chloro 2-methyl pentane. So I do have to switch out the bromo and the chloro there as well. Sorry about that. But the naming's pretty much the same kind of convention.
Professor.
Mm-hmm.
So for this type of question, we take the reactant and then we rotate it so we have the hydrogen in the back. Then we name them after we find.
Nora, I have to be real clear about this. I have to be real clear. Locate the hydrogen, which is the lowest priority group, and switch it. Don't rotate it. Switch it.
Switch it. Okay.
Switch it with whatever's currently in the back. That will have the effect of creating the compound that has the opposite configuration. In addition to that, you also have to substitute the 2 atoms as well, and then you find the stereochemistry of the product, and you then deduce the stereochemistry of the reactant, knowing that it's opposite stereochemistry to what you found for the product.
Okay, and then we substitute because it's SN
Or
based on SN1 or SN2.
That's what the S stands for. Yeah.
Okay. All right. Thank you.
All right. Okay. Any other questions?
Where does the R and the
Nora,
S?
sorry, Nora. Could you please mute? Thanks. Sorry.
Sorry. Where does the R and the S go when you name it?
At the front.
So like 3R?
Yeah, or well, actually, I just ran out of room here, Deanna. I'm sorry. Let me see if I can make myself a bit more room here. Whoops. I'm not a real fan of this paint, but anyway, I'm going to have to delete some of this stuff here. Select. So for the first one, I would name it R3 Bromo. See, I just put the R out the front. 2-methyl pentane. And of course, the other one would be S3-chloro, 2-methyl pentane. I said earlier, you have the option. You could put 3R at the front if you want, but you don't have to because there's only one chiral center.
Are they supposed to be in parentheses?
No, they're in parentheses when you've got 2 of them.
Okay.
And you can put them.
It's fine.
Yeah, but you can put them in parentheses if you want, but the convention is usually not to.
I have one more question.
Mm-hmm.
So the one that we did when we switched everything, you named it S.
I did. Yes, Deanna, I did. But it was S3-chloro 2-methyl pentane.
Is that because that structure received the substitution?
Yes.
Okay.
And it's got the lowest priority group in the back, so I can actually assign a stereochemistry to it. That's the whole point. See, at the beginning, I don't have the ability to do that because the lowest priority group isn't in the back.
Okay.
And of course, the other piece of information is that by switching 2 groups, we always change the stereochemistry. It always reverses. All right, any other questions about that?
When you were clarifying for Nora, you had kind of, the end of it went a little fast for me.
Okay.
That you said, locate the hydrogen, switch it with what's in the back. That is the opposite configuration. Then you substitute, in this case, the chlorine for the bromine. And then this is the part I didn't catch, you reverse engineer the stereochemistry.
You deduce the stereochemistry of the reactant knowing what the stereochemistry of the product was. That's the part I really want people to understand. And it's the part that people usually don't understand. They understand the words I'm saying, but they don't get what I'm saying. And I want people to understand that. So, whatever it takes, whatever questions you have to ask me to understand that, that's what I want you to ask.
So how do we know that the methyl group is moving to the right? Like, how do we know it's moving position?
Well, what I did there was, you're talking about this grouping here, the this isopropyl group. Is that what you're talking about?
Yeah, sorry.
Yeah. So what I know is that's in the back, but what I need in the back is the hydrogen. So that's what I did. I switched the hydrogen with whatever happened to be in the back at the time.
Oh, okay. I got it. I knew that. I was just like, did we rotate it? But the whole thing didn't rotate, and it's just different because you have the 2 coming off of it.
But I switched them rather than rotated them for a specific reason, and that was to obtain something that was going to be the exact opposite stereochemistry to what I started with.
Okay.
So, this is the whole point. I'll spend as long as you guys want here on this. I want you to understand. I don't want you to sit here and say, well, look, this is only 10 points. I can miss out on 10 points on this test and I'll be okay. I don't have to understand. This is all too hard. Dr. Musgrave is just crazy, and I don't really need to know all this. I'm just going to blow this question off, or I'll just fly by the seat of my pants and I'll make a guess at the end. I don't want you to have to do that. I actually want you to understand it. So ask away, ask your questions, figure it out.
Dr. Musgrave,
Yes.
how did we know that this is SN2?
Because it said so in the question. I'm sorry, Mariah, it got kind of cut off here. Do you see that?
Okay. Oh, yeah, I see it. Thank you.
Yeah. It's in the, it tells you in the question, is the bottom line. All right, any other questions about this one?
I think it's just, at least for me, just like a matter of like seeing more to see how it all like comes together in different problems, you know what I mean?
Mm-hmm. Mm-hmm.
Professor,
Yeah.
so this question has one product. Are there other questions that will have multiple products that we have to draw?
Yes, Nora, there are. That's the SN1.
Okay.
And I was actually going to do SN1 for this specific one, which I will do in a second. But I want to make sure that people understand this one first before I move on. Okay, so any other questions about this specific SN2 example? If nobody's asking me anything, then I'm going to have to assume that you completely understand everything I've been talking about.
I have a question, but I don't know if I'm wording it right.
Okay, go ahead.
So for anything that gets labeled S, is because that's where we did the substitution, not because of the way that we numbered it, or both?
No, it's because of the way we numbered it specifically.
Okay. All
And
righty.
the fact that it went 1, 2, 3 counterclockwise. That's why I specifically named it S.
Okay. Thank you.
I'm a little unsure on what my question is asking, but like I understand what you're giving right here very well. I think I understand what you're trying to say. I don't feel steady in the other R and S portion that you taught earlier. I think it's kind of making me confused with this, with the rotating versus just switching. And I'm not really sure what I'm trying to ask, but that's what I'm confused on a little bit.
Me as well.
Okay, so in the other question, which I will go over examples of those as well. We have some time, you know, that's the thing. This is the last problem we have to talk about. So we've got today, and I think we've got Monday as well, you know, for review. So, you know, we've got plenty of time to try and get these issues sorted out. But in number 5, the focus mainly is on rotating. And again, we're rotating to get lowest priority group into the back. And the reason that it's different for number 5 is because we want to maintain the stereochemistry. I'll say it again. We want to maintain the stereochemistry. Here, I'm playing games. I'm doing tricks. I'm doing backflips here. Why? Because I want the opposite configuration. Whereas in number 5, when I'm initially trying to get the stereochemistries, I don't want to change the configurations. I just want to get just want to rotate it. Okay, so somebody else had a question. Yeah, Nora?
Okay, so previously we were trying to find the stereochemistry. That's why we rotate to find the lower priority, to find if it's S or R, right?
Well, to put the lowest priority into the back, to be clear, Nora.
Okay, and that will tell us if it's rotating clockwise or counterclockwise.
Right. Well, with the priorities, yes.
Yes, and then for this part, this one is we're switching because we want to find the products.
And the products we know are the opposite stereochemistry to the reactants. Why do we know that? Because I said so.
In the question, or you said so right now?
Right now. Do you see this?
Okay.
I'm circling it right now. See this?
Well, but what happens in reality? Is this what happens to the actual molecule?
Well, no, what happens in reality, it's kind of this, but what happens in reality is the Cl comes in from the back and kicks out the Br from the front. That's what happens in reality. But the effect is that we end up with something that is of opposite configuration to what we started with. I mean, when Cl comes in from the back, it turns it inside out, which means it switches the stereochemistry. The way that I'm solving, look, that's the way I'm solving the problem. It's not the only way. There are millions of ways to skin a cat. I could choose other ways of solving this. I think this is the easiest way. You might not agree. You might decide that there's another way that you want to choose in order to do this. And I say, do it. If you think it's easier, then you should do it. I challenge you to. I don't think it is. I think this is the easiest way of doing the problem.
It looks like it's one of those problems that the more you do, then better it gets. So examples go better.
yeah, that's right. All right, so any other questions about this one, though? I really want to see if I can clear up any confusion anybody has about what we're doing here in this problem.
So does rotating it change the stereochemistry of it?
Absolutely not.
So then why couldn't we have, I'm still just like,
well, look,
mixing the two things up.
Yeah. Well, look, the thing is, everybody except Jonathan, I want you to close your ears, okay? Because what I might say might confuse you. So I'm going to just talk to Jonathan now. Everybody else can put their hands over their ears and go la, 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 right? Another approach you could take, Jonathan, is I could actually rotate this one, leave the Br where it is, put the hydrogen where the isopropyl group is, put the isopropyl group where the ethyl group is, and move the ethyl group where the hydrogen is. That's rotating. But in so doing, I do not switch the stereochemistry of that specific molecule.
So the hydrogen goes to the back, the isopropyl comes to the front, and ethyl is normal.
Ethyl will,
right?
Yes, that's correct.
Okay.
And now in so doing, that would give me an R configuration.
That makes so much more sense.
Okay, but if you know that that is R, then the product would have to be S, and you'd still have to draw the product.
That's all right.
And it couldn't be just a direct replacement of the Br with the Cl, because it would still be R.
Oh, I see. So you'd have to switch up the stereochemistries again.
Gee, I wonder how we might do that, Jonathan. Have you got any ideas? Any ideas about how we might switch the stereochemistry? Any thoughts about how we might achieve that?
By changing places.
Oh, by switching two groups, perhaps. How about we do that?
Okay.
Or how about we make our lives easier and actually get the lowest priority group into the back and do the substitution at the same time?
We're hitting all the birds with the stone
You're
this
a
time, guys.
genius.
This is great.
There we go. There you go.
Even though it's more clear now, can we still think you're crazy?
Yes, absolutely.
I think it's just like been a kind of visual thing for me. I think I got it.
Okay. Yeah. That's all right. That's all right. I know I'm being really sarcastic, and I apologize for that. But I think it was worth the effort. I do.
Yes, I appreciate the mic drop. It makes class more interesting.
Okay. Does anybody have any questions? Any other questions about this one? All right, let's do this one. Now what I'm going to do, I'm actually going to do this problem again. I'm going to, just to annoy people, I'm going to switch that out. Now I am just going to do this one for SN1. I repeat, I'm doing this one again, but I'm doing it for SN1. Right? SN1. Here we go. Means I have to delete some stuff here, which I will do. I'm going to try and enlarge my canvas here. All right, that will go a lot better. Okay. So everything else still applies here. I don't want to erase any of this other stuff, but you know, I will. Anyway. Okay. Anyway, the whole point with the SN1 is that you're going to get two products. So Nora, I think you were asking this earlier. SN1 gives two products, and it doesn't matter if it's R or S that we start with, we always end up with R and S products. So let's see how we might go about doing that. Now, the method that I'm going to show you here is actually pretty similar to what we just talked about. It's just split over two compounds. Okay, so let's see what we end up with here. Right, remember we're doing the same thing, but we're doing it for SN1. Okay. So we know that we're going to end up with something of the same configuration as the reactant and opposite configuration of the reactant. So in order to get the one that has the same configuration, it's easy. I just do what I call a direct replacement, which means I just replace the Br with the Cl directly, which I know will give me the same configuration. Then I know I'm going to get a second product, and this second product is going to have the opposite configuration to the one we just made. And it makes sense when I'm making this opposite configuration to go ahead and do it so that the lowest priority group ends up in the back.
So quick question, can we
Yes.
do that for anything? Can we just switch it out instead of doing that whole rotating crap? Because the rotating crap is what confuses me versus the substitution.
Right, but understand that I didn't do a rotation just now. I did a switch.
A switch, yes.
Yes.
Mm-hmm.
I want to be real clear about that. Rotations do not change the stereochemistry. Switching changes the stereochemistry.
Gotcha.
So I have a question.
Mm-hmm.
It looks to me here like we're getting something from nothing. Where is this second molecule coming from?
Well, I'd have to go back to the initial explanation that we did on Monday for this. And the idea is that the bromine comes off and we end up getting this planar carbocation, which I'll draw here. So the first thing we get is this. So the bromine comes off, and then the Cl- can attack from either side, which is why we get two things of opposite stereochemistry.
So this isn't like a basic reaction format like we've seen before. This implies something else.
Well, it implies SN1 and SN2 processes, which we've been talking about in previous.
Well, I'm talking like, you know, sorry, Gen Chem 1 and 2.
Oh no, this is something you'd never have seen before in your life.
Right. Yeah.
I don't think, unless you're a really advanced child. No, I don't think so. You've seen it before. I remember doing this in first grade myself. I'm just kidding. Just kidding. All right. Anyway, any questions about getting those products and how I got them? And can I just reiterate something here? If you look at what we know about SN1, and this is what I put the arrows on here, R gives R plus S. So we know that we get something that's the same configuration and the opposite configuration as what we started with. And it doesn't matter if we start with R or S, we're always going to get the same and opposite. In order to maintain stereochemistry, I do a direct replacement. To switch the stereochemistry, I switch two groups. And it makes sense when I switch two groups to arrange it so that the lowest priority group ends up in the back. Does anybody have any questions?
So for this problem on the test, are we also assigning the S and R and naming it?
Yes, that's correct. At this point, I just wanted to make sure people understood how I get the products. Okay, so let's look at this. Since you mentioned it, Mariah, we'll go to the stereochemistry. So the priority is going to be the same. It's going to be 1, 2, 3. So this would be S. because I switched 2 groups to get to S, I know that this one must be R. Everybody clear on that? Is everybody okay with how I get R for this one? I don't get it by assigning priorities. I get it because I switched 2 groups to get here.
Could you do that one more time? Sorry.
Right. So I figured out this was S, but the way that I got this S compound was by switching 2 groups on the previous compound, which means it has to be R.
And you know that one is S because it has the lowest priority in the back.
Right. And then the 1, 2, 3 goes counterclockwise.
Counterclockwise. Okay. Thank you.
All right. And if the other product is R, it means the reactant must also be R.
So all S's have lowest priority in the back?
No, anything you're assigning stereochemistry to using priorities will always have the lowest priority thing in the back. This is S because the priorities go in a counterclockwise direction. 1, 2, 3 counterclockwise.
There was a diagram earlier, I think, in the slideshows where you put the S in one side and then R's goes in the other side. That's where it's coming from, right?
Right. Yeah, but again, in order to assign stereochemistries, the lowest priority group always has to be in the back.
Yep.
I have a quick question. So when you were writing out the rules for Sn1, you said R gives R plus S as well as S gives R plus S. So why in this instance is it R in the reactants?
Because R can give R plus S or S plus R. S can give R plus S or S plus R. It's commutative. Keisha?
Oh, okay.
So
I think he's trying to figure out why the reactant is R instead of S, since both of them make R and S.
Yeah.
Okay. The only reason I know that the reactant is R is because I got the R that I'm pointing to with the arrow right now.
And it's in the same configuration.
By doing a direct replacement, which did not change the stereochemistry.
Right. So technically, because it's the same thing. It's...
Not technically, Keisha, because it is the same thing.
Okay, I got you. Thank you.
Then it maintains its stereochemistry.
That makes more sense. Thank you.
Does anybody else have any questions? Actually, you probably don't dare ask a question at this point. All right, but seriously, does anybody have any questions about this? Because really, I want you to understand exactly what I did here. I know it seems like magic, but, you know, it isn't. It's chemistry.
To bring it full circle, earlier you were saying you really, really, really wanted us to understand that we deduce the stereochemistry of R based on what the product was. So this is kind of really using that, correct? You're looking, you find the S.
Absolutely it is.
You work your way back to what the other one is, the R, and then you go back to the original and you can see.
Yeah, but Rebecca, in that same vein, realize that the SN2 is kind of doing both things that we're doing in the SN1 just at the same time on the same molecule. But in the SN1, we're doing a replacement on one and a switch on the other.
Okay.
Do you get what I'm saying with that?
It's almost like the SN1 is divided out where the SN2 has it just all together. It's right? Okay. I will take your nonverbal as a yes. Thank you.
Yeah, that's what I wanted to hear. That's cool. All right. Anybody else got any questions about this?
So we switched the chlorine with the bromine because bromine has the highest mass?
No, we switched the chlorine with the bromine because bromine's the leaving group.
How do you know it's the leaving group?
It's always a halogen.
Oh, okay.
The C's are horrible leaving groups as C negatives. I can tell you that. The leaving groups leave because they're relatively stable with negative charges.
Thanks.
So I'm trying to understand why it's actually happening, like in real life. Why would the bromine leave for the Cl to come in the first place?
Because the compound, this thing I'm pointing at here with the arrow, this carbocation, is somewhat stabilized by the fact it's got 2 carbons connected to it. So when this bromine just pops off, sure, but only maybe 1 in, say, 1,000,000 might pop off, right? But once that carbocation forms, the Cl- can attack it. And then another one can pop off, and another one, and another one.
Okay, so what you're saying is out of a sample of many, many molecules, a few of them will go through this process.
Yes, but by Le Chatelier's principle, they'll get pulled through they'll all get pulled through the product in the end eventually.
Right. Okay.
Right.
So it takes time.
It takes as much time as it takes. You know, it all depends on equilibria and everything else, but yes, it takes time. All right, other questions? Any other questions about this? Now, sorry, Nora.
So my question might be like a first grader's question, but I'm having a hard time seeing the front from the back on a picture. Like I just really, my geometry is very bad. So you're rotated to the back. How did you know the back is this and not the bottom? You know what I mean?
Because the dashed line is always going to be the back, Nora.
Okay. So
always.
that's like
Yes.
a given?
Yes, given.
Okay. So every time you see a dashed line in that sort of question, that's the back. So what's that what's the 3D line next to the dash? What does that tell you?
The other thing's coming out of the page. It's in the front.
Okay.
Now the other lines that are just regular lines are in the plane of the page.
Okay.
But you know, I've got my little thing here. Can you see this? No, you can't see this, or maybe you can. Oh yes, you can. Can you see me? I don't know.
Yes.
Can you see me? You can. Okay, right. So can you see me holding this molecule?
Yes.
Okay, good. All right, Nora. See this? No, I have to look at it the way you're seeing it, though. It seems like the yellow's in the front, right? Would you agree with that?
Yes.
Okay. That means that would get the solid line. This black one here is in the back. That would get the dashed line.
Okay,
and this blue one would just be a regular line, and this red one here would be a regular line.
Okay. So that means the blue one is the hydrogen.
Oh, not necessarily. I'm just giving you an example.
Yeah. Well, referencing back to the question.
Mm-hmm.
Okay. Okay.
Well, in this instance, oh yes, the blue one is where the hydrogen would be in this question. Yes.
Yeah, that's what I was.
Yes, I would agree with that, Nora. Yes.
Okay.
And that's not where we want the hydrogen, though, right?
We want it in the back.
We want it in the back. We want it where this black one is, right?
So how do we switch them up?
How do we get it there? We switch it, right?
Yes.
But by switching it, what did I do to the stereochemistry, Nora?
You changed it.
I changed it. I reversed it, didn't I?
Yes. You did.
Yes. Yeah, thank you for asking that. Now, here's the other thing. Jonathan, I'm doing this for you. What I just did, switch to stereochemistry. See what I'm doing now? What am I doing now, Jonathan?
Moving it?
No, say it again. Rotating it. Thank you. I'm rotating it. Am I changing the stereochemistry by doing this?
No.
No.
Absolutely not. See? Look at that.
Amazing.
Amazing. All right. Other questions? Other questions?
Can we name them now?
Oh, sure. Let's name them.
Okay. Perfect. Thank you.
It'd be, well, it's the same names as what they were before. So it'd be stop. 3 bromo 2 methyl pentane. And the products here, this would be 3 chloro, 2 methyl pentane.
Because it's the same stereochemistry and all that.
Yeah.
You just changed the chloro there.
Yeah. Yeah, that's exactly right. Whereas the other one here is S, the same thing.
Okay, for the complete answer, we need to draw all products and reactants and name all 3.
Absolutely.
Okay.
All right. Other questions?
Just a question about the test. Will we be given that sheet again that's got the like methyl and stuff like that on there?
No, unfortunately.
Okay.
But well, you know, but I don't actually give a lot of credit for getting the correct name. It's more about my main focus in that question is about stereochemistry. I might assign a maximum of 2 points to a name, you know, getting the name correct. So
Okay.
yeah, I still think you should know though, Sierra. And usually though, I don't usually include anything that has anything more than say isopropyl. That would probably be it.
Okay, gotcha. Yeah, like I know majority of them. I just feel like on tests I get like frazzled.
Mm-hmm. Mm-hmm. All right. Any other questions?
I know everybody's ready to move on, but just hopefully this will be fast. In the original naming, how did you name the 3, I'm sorry, the bromo 3 and the methyl 2? Did
Okay.
you also?
What I did was, no, I drew a line structure. Rebecca.
Oh, right. Okay, I remember. Yes, I have that down. Okay.
I'll just redraw it here for kicks.
So we would need to do that because I can't see it looking at these structures.
Yeah, I think
if it's not readily obvious to us, then we should draw the line structure and then we can name it. Okay.
Yeah, that would be my answer.
Okay.
It's not a pretty thing to have to do, but you know, it's one of those things.
Okay.
All right, any other questions? All right, let's do another example. I'm sure you're all, I know Sierra wants another example.
Yes, I do.
I do too.
All right. Okay. Let me see what we can do here. So just moving over. Let me see what we have here. I'm just going to pull up another test here. All tests. Okay, let's see. I'll do fall 2018. Oops, I don't want that. Let's do this. Okay, looks like it appeared where it was supposed to appear. Okay. Let's go down to the band. Here we go. All right, here we go. Oh yeah, I like this one. This is good. All right, there you go. Here's the problem. It says here, draw Sn1 products. So we need to do Sn1s for this one. Now, generally speaking, I usually give something that's secondary so that it could be either Sn1 or Sn2. Okay. This one is secondary. All right. So Sn1, I want you to, I want a bigger screen here, so that's why I'm going to. obscure that SN1, but that's what we're looking for.
Would the salt be taking the bromine's place in this problem?
Well, the Cl will, yes.
Or the Cl?
Yeah.
Okay, because Na would be, it would dissociate and then the Cl would come into the...
Yeah, so we...
All right.
Yeah, so somebody, I think Julie had asked about this the other day. How would you know that? Well, you'd have to know that NaCl was an ionic compound and it splits into Na plus and Cl minus, and the negative part is the part that has to react.
And Na plus, because it loses that one electron, now it has 8. Or now its electron shell is full and it doesn't want to react with anything anymore.
Right, and it would be a spectator. It would be Na plus at the beginning, Na plus at the end.
I do have a question, too, actually. So is it assumed that all of these reactions will occur in water?
Well, yeah, I suppose, but it could be any solvent. But
Okay.
we're not limiting ourselves to water necessarily.
Sure. So then if the Cl takes the place of the bromine in this one, would another product be NaBr?
Yes, but you wouldn't have to. I'm not interested in that product. I'm only interested in the carbon products here, to be clear,
Okay.
Jonathan. But yeah, sure, you could do, but it would be really Na plus Br minus, wouldn't it?
Sure, Na plus Cl minus.
Which is why I'm saying Na plus is a spectator, because it's Na plus at the beginning, it's Na plus at the end.
Right.
Now we're doing SN1 here, which means we know we're going to get 2 products. So I'm going to do a direct replacement, which means I'm just going to replace the Br straight with the Cl and not change anything else. So I want you all to understand that when I did that, I did not change the stereochemistry of anything.
You're very clear.
Thank you. And I'm going to draw the other one below it. And I know that whatever else I'm doing now, let's see, I need that hydrogen in the back. So let's see, the Cl will stay where it is. I'll put the hydrogen into the back. And the other group now, let's see, have I got, I don't think I've got enough carbons there. C1, C was 1, 2, and then the, yeah, okay. I know Julie probably hates this if Julie's on the call. I don't know if Julie's on the call, but if she was on the call, she'd be screaming at me right now and saying, that looks so different.
Well, you definitely changed the structure of it.
Yeah.
I mean.
All right. So let's talk about that. Talk about what I just did there and why I did it. Does anybody have any questions about that?
Yes,
yeah.
I have a question. I think I understand what you did there, but I'm not sure. So that part that you just changed at the end?
Yeah, well, I know I needed the hydrogen at the back, right?
Right.
But what's presently at the back is this 2-carbon structure with an isopropyl group attached.
Right.
So this entire thing that I'm going to circle here.
I think you just answered my question, because I wasn't seeing how it was an isopropyl, but then there was, to me, in my mind, there was like an extra line there, but that's the 2 carbons.
Yeah, you see, it confused me initially when I drew it. Remember, I had to correct myself as I was drawing it.
So is that like isopentyl, if that was not part of the parent chain?
Isopentyl, yeah, I'd say it's isopentyl, sure. All right, any other questions? All right, so I switched out that group that's at the back with the hydrogen in the front. Now that I've got the hydrogen in the back, I can now assign priorities. So number 1 will be the chlorine. Number 2 will be this group because it's got the branch on it. And number 3 is the straight chain.
Do halogens get first priority?
Well, whatever has the heaviest atomic mass gets priority. CL, okay. It's based on Cl, C, and C. And since Cl is bigger than C, then it gets first priority. When comparing the other two, it's based on whether one branches or not. Branching always increases the priority. So this would be R. Now, I haven't done a name yet. I'm just going to call it R. I'll put the R over here. Okay. And I'm calling it R because the 1, 2, 3 goes in a clockwise direction with the lowest priority group in the back. Any questions? So if that one's R, it means the other one automatically must be S, because I got the R by switching 2 groups from that previous example.
That would make the reactant R?
No.
It would be S.
It would be S because it would have the same configuration as the one we just made.
Oh, yeah, I see what you're saying. Thank you.
And we know that because all we did to go from the arrow one here to the arrow one here was do a direct replacement, which did not change the stereochemistry.
Okay, so in the R formation, it's that group is second priority because it's got a greater mass on the other side. Like, I know you're taking it one atom at a time, but aren't they all carbons?
Yeah, but one's branched. So look. Okay.
Oh, and the other one's not. Okay.
Right. So it goes this. So C, no winner. C, no winner. C, no winner. But this C has 2 C's connected to it, whereas this C's got a C and an H connected to it. So this one wins.
Seems like I need to review that a little bit.
Well, yeah, it's something we talked about when we went through with the easy stuff. Right?
Yeah, it seems like a while ago.
But it was part of this test, right?
Yeah, it was.
I'm not pulling stuff in from other places here.
Oh no, definitely not. I just need a refresher.
All right. Any other questions? All right. Now the naming part. Why don't you all see if you can name it? See if you can, just a name. Don't worry about the stereochemistry, just a name. See if you can get
which item.
Well, they're all the same. Well, say the reactant. We'll say the reactant. Yeah, you're right. They're not all the same because they have bromos and chlorine. So we'll do the reactant. All right. See if you can figure out the name of it. Somebody needs to mute. I'm not sure who, but somebody does.
Is it S5 bromo 2 methyl ethylene?
Well, let's have a look. Let's have a look. I would first of all draw a line structure for this. And that's what it would look like. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a decane. And it's 2-methyl, 1, 2, 3, 4, 5 bromo. So 5 bromo would be first for the alphabetization. So 5 bromo, 2-methyl, decane. Oh, you don't like that much, do you?
Wait, it's 5 bromo, not 6 bromo.
Well, I'm looking at the counting here. Be 1, 2, 3, 4, 5, as far as I can see.
And you
I
did
was
that
going the
because
other
there was
direction,
more
my bad.
stuff on the left side. Well, you have that methyl off on the left side, and nothing really on the right. Or sorry, on the right and nothing on the left.
Oh, this is why I had to number it from that direction. Yeah.
Yeah.
Yeah. Oh, okay. I think that must have been where the 6 came from, right?
Yeah, I started at the left, but
Yeah.
I forgot that that was a methyl group.
Yeah. Oh, something else to review.
Yeah, let's just say I didn't do too hot on the first one and definitely got to catch up.
All right. Anyway, there you go. Any questions? Sorry.
I'm interested in how what looked to be like a butyl group or an isopropyl group, and then I did draw the line structure the way you did, but then I stopped because I was like, wait, I lost my group because I was just going up and down with the C's. Is that okay?
Absolutely.
I mean, it looks like it changed to me, but maybe it didn't.
It didn't. It didn't. And that's the thing. It looks like you're losing groups, but you're not. It's just that they're becoming enmeshed in the base chain.
Okay, got ya. Okay. Is it sort of like when we were naming and we were looking for that longest contiguous chain, and now we're doing it as a two-dimensional?
Yes.
Okay.
Absolutely. Absolutely.
Then I'm okay with losing them.
Yes. There you go. All right. Ooh, great. Yes. All right. Any other questions? All right, let's talk resources over here. And I'm going to have to pull something over here. Ooh, I didn't want to pull that over. Hang on. I didn't want to have to pull that over. Hang on. Let's do this again. I want to pull the whole thing over. Here we go, not just a window. There we go. All right. So in the blue book, remember this has got all of the practice problems in it. And I had told you previously that we have 35 examples of the ones I just showed you. 35 that you can do. So these are all in order. This is number 6. There's 35 of those. And let's see, keep going. Here we go. And this is number, let's hop back here. And yes, so starting here on page, looks like 29, we've got all of the ones from 8, and there's 35 of those. That with answers.
Is this in like a practice test, like study guide file?
It's in it's problems. It's the problems test 2 file in the test 2 folder.
Okay, thank you.
If you have the blue book, it's that. Okay, some people have the blue book, some people don't. If you don't have it, then you can just download the file from here. But that's where you'll find all those examples. I think that's something some people missed from the first test. They didn't realize what that was and that there were practice problems in there that they could do. But I'm trying to be real clear about that. All right, any other questions? So everything is in one place, and that's the place it's in. It's in that thing, which is actually the blue book, which you can get from the bookstore, or you can download these files from the test folders. All right. Okay, other questions about this? Okay. So what I'll do is we'll start reviewing now, and I'll start back from number 1. I'll be honest with you, I don't know if I'm going to be spending a lot of time reviewing this one we just did, since I feel like we did a lot on that today. But let's go back to the first question here, and I'm still in fall 2018. And there's our question for question 1. So question 1 is when we're looking for easy or neither. And just by way of review, I'll show you how we would go about doing something like this. And this is where we first latched on to the concept of priorities. So for something like this, I never give line structures for these, but I'm going to go ahead and, well, yeah, I'll draw it out as a line structure. Looks like it's 3. So 2, just a C and another C here. This one is going to have, if you want to, you can do this too. You can draw it out as a line structure if it helps. Some people it doesn't help. But that would be that one as a line structure. And, we draw our stuff down the middle here in the middle of the double bond. Then we have to figure out which one gets priority on each side. So it'd be C, no winner. It'd be C, F. So that would be the winner. So that's number 1. That'll be number 2. Then on the other side, C, no winner. F, C. And that means that this one is the winner. So it'll be 1, that'll be 2. So this one would be E. So when the ones are opposite, it's E. When the ones are on the same side, it's Z.
Z same.
Z same side, that's exactly right. Now the other one, actually I'm not even going to draw this out, because what you can see is if you look on the right-hand side, you've got exactly the same groupings coming off that carbon. That tells you it's going to be neither. I mean, if you can't figure out what the priority is because they're the same, then it can't be E or Z. All right, anybody get any questions? Okay. Draw and label cis and trans isomers of 1-bromo, 4-ethyl cyclooctane. So for this one, you would draw, well, I'm just going to draw both of them, but it's a cyclooctane, which means that it looks like a stop sign. Sometimes you can draw the one that doesn't have any stereochemistry just to be sure of where the positionings are. But we've got 1-bromo, 4-ethyl. So if I put the bromo up here, and we'll make this one cis to begin with. So we'll put the bromo here, and I'll stick it out of the page. See, 1, 2, 3, 4. So the ethyl group goes down here. And whoops, we want cis, so it has to be pointing out of the page as well. So that'll be 4-ethyl pointing out of the page. And the trans is just going to have one of those as pointing down. It doesn't matter which. So I'll do the same thing. And the cis 1, 2, 3, 4. The cis is the same. So that'll be trans. All right. Any questions about that? So that's for number 2.
Yes, I have one.
Mm-hmm.
So the pointing out is the one that that's the thick one. Let's just call it that.
That's right. But the fact that they're both pointing out is what makes it cis.
Okay. And
for the trans one, the one's dashed and one's out.
That makes it trans.
Yes.
Okay. So you can't put 2 thick ones opposite directions and call it trans?
Correct.
That would not work?
No.
Okay.
No, you have to be very strict about it. You have to say
Okay.
that it doesn't matter what direction they're pointing. What matters is whether they're wedged or dashed.
Okay, so wedged is cis and then dashed and wedged is trans.
Both wedged is cis or both dashed is trans. One wedged and one cis is trans.
Okay. Okay, that makes sense. Thank you.
One wedged, one
I'm
dashed.
sorry, did you just say both dashed are trans?
No. No,
Okay.
both. Okay, but both wedged or both cis are trans. One wedged and one dashed is trans.
Okay. The words cis and dash keep getting confused.
Oh, sorry.
Yeah.
That's all. If they're both the same, they're cis. If there's one of each, they're trans.
That's right. Yes, that's right. So let me say it again. They're both wedged. It's cis. They're both dashed. It's cis. One wedged, one dashed is trans.
Now say it 5 times fast.
No. I'm not saying it again. I'm not saying it again. Okay, so that's number 2. All right. Any questions? Any other questions? Okay. All right, let's look at number 3. Now, number 3 is this Newman projection question. So we're going to prepare a diagram here. And that diagram is going to look like an energy diagram here. It's going to be E, and down on the bottom here we'll have degree of rotation. And this will be numbered in increments of 60. Hopefully relatively even increments of 60. Not very pretty what I'm doing here, but effective regardless. Okay. Then we start drawing our Newman projections. And the way I would handle this is the CL is at the front, and the C with the CLs, the C with the CL has 2 hydrogens and a CL pointing upwards. And then at the back, we know that the configuration looks like this. And we'll have 2 hydrogens at the back and an isopropyl group at the back like that. So that's what I should be drawing. That would be anti. And that would be down here on the energy diagram and labeled anti at 0. Any questions? Okay. So then we move it around 60 degrees. And I can choose either to move the back or the front. I'm actually going to leave the back the same and move the front. So the back is going to stay the way it is. And I'm going to move the front around 60 degrees. And this would be what I'm calling E1 or eclipsed 1, which is going to be an eclipsed structure. So it's going to be higher energy. So that's what I've got so far. I move it around another 60 degrees and I get my gauche. And again, leave the back the same. And let's see. So where's the CL end up? The CL end up down here. And that would be gauche. Now that's a staggered conformation that's a bit higher of an anti, but it'll be down here. There's gauche. So that's E1 there. This will be gauche. So the anti is here. The gauche is here. And then the last one is the eclipse 2, which is where the Cl will actually be eclipsed with that large group. And this will be the E2. So that's the highest energy one, and that's at 180. That's going to be up here. And then the rest of it just mirrors. This is not a very good diagram, but anyway, there you go. But that's at least those things are correct there. The Newman projections themselves. That's what it looks like. All right, any questions about number 3? Again, practice the ones in the blue book and practice the ones on the old tests. All right, we'll leave it there for today. And I'll see some of you in about 15 minutes in lab.
Thank you.
Thank you.
Bye.
Professor,
Yes, Nora.
I have a quick question. So I watched the videos for the Newman projection. I don't understand it very well. I mean, what you did here makes sense if it applies to every compound we get, but I want to understand it, but I'm not sure I do.
Okay. Well, what do you want to do about that? You can we can set up a Zoom session. We can talk about it.
Can we just like
Yeah.
15 minutes? I don't know.
It's just not right now.
Free. Yeah, not right now. It's fine. I just want to, because if this is the structure that applies to every compound, I could do that from memory. I just want to understand how it came about. You know what I mean?
Mm-hmm.
Okay,
Sure.
I just really need that clarification.
Okay. So send me an email. We'll set up a time.
Okay, thank you so much. Have a good day.
Okay, bye, Nora.
Bye.
Natalie, did you want anything from me?